Hi class, for this lecture you're going to need the table, so click on this link which is going to take you here, and then let's take a look at the handout. So here's the basic idea on the handout. So we're going to be performing hypothesis tests for the standard deviation or variance. It could be for either one of these two, but the actual tests are only performed, or in terms of the notation, on the standard deviation. So if you're given a problem that you're given that sigma squared is greater, less than, equal, or not equal, or any statement to a value of k, we would actually take the square root of both sides. So basically sigma, after you take the square root of these two, if it says greater than k, and then you're going to end up with sigma, it's greater than plus or minus the square root of k. Technically sigma would be greater than the positive root of k. And we're always using the positive because technically your chi-square distribution, it's always on the first quadrant. So I'll write it out with this notation because that could show up on the homework assignments. So if it says variance, you're always using technically the standard deviation, which is the square root of it. And this is what our regions are going to look like. In addition, for this type of test, this is going to be your test statistics. P-values are going to be obtained either from the table, or you're going to be using the chi-square CDF, and you still have the same idea that if there's a claim that is less than, you're going to be looking at a left tail test, equal, not equal, two tail test, and then a greater would be a right tail test. Wait, I said this one wrong. If it's less than, this is the corresponding shape. If it's greater, this is the corresponding shape. And then for equal, not equal, it's this one. I think I messed that up. Okay, so let's take a look at the first problem. And on the first problem, we're just given the following information. And in this case, the actual claim is in terms of the variance. So what I'm going to do is I'm just going to rewrite it. The variance is greater than 225. So I'm just going to take the square root of both sides. And technically, this causes a plus and minus in terms of algebra. So you would have the sigma, it's greater than plus or minus the square root of 225. Or sigma is greater than the square root of 225. Please evaluate that. I think it's an integer. So square root of 225, I'm getting 15. So sigma is greater to the values of 15. We would always use the actual positive value. The result of taking the square root does provide a plus or minus, but because your distribution is always on the chi-square distribution is always positive, no need to use the negative. So we're going to start with the claim, and it's going to have the same outline that we did before. So in this case, here's your claim. I'm just going to rewrite it as a standard deviation. So the values of sigma. So the claim is that the values of sigma happens to be greater than the values of 15. That's after we take the actual square root. And then the next step is going to be to state HO and the values of, they're calling it an H1. So in this case, we're going to have that HO, the values of sigma are equal to 15. And then the claim given in here is that sigma is greater than the values of 15. Now I'm just going to use the classical approach. We'll do the p-value. We don't have the shortcut for the p-value, so we would have to evaluate that code with the chi-square CDF. The next step is the critical value. Now, for critical value, we're given that alpha is equal to 0.10, which means E is equal to 0.90. Furthermore, N is equal to the values of 21. So degrees of freedom are going to be 20. And let me box the degrees of freedom. Remember that degrees of freedom for the chi-square distribution is n minus 1. So when we look at the population, this is what it's going to look like. Because the claim of a grader, it's going to be a right tail test. Let me draw the chi-square distribution. So it'll look a little bit bell-shaped. In any case, it's going to look like this. So we're only going to have a chi-square value on the right-hand side. And because of the right tail test, this is 0.10. And this portion is 0.90. So at this point, we're going to take a look at the table. And we're looking for a chi-square value that has 0.10 to the right with 20 degrees of freedom. So from the table, this one has 10 to the right and 20 degrees of freedom. So it's going to be the 28.4112. So we're looking at this value here. 0.10 to the right, 20 degrees of freedom. Let me double check, 28.4112. So in this case, this value is the 28.4112. And let me just rewrite it here that this is the critical value. So 28.4112, it's going to be our critical value. And I'm just rewriting it so that we don't somehow confuse it with the test statistic. Now, the next portion, it's going to be for us to evaluate the test statistic. And this is going to be a chi-square value that has the following format. So let me rewrite it. So our test statistic, it's a chi-square value that has the n minus 1. So n minus 1 s squared over the variance. Let me double check. There is a typo here, but it's supposed to be a chi-square value. And then our values are 21. So this one will have the values of 20. S, it's going to be 64 squared. And then we're using the variance. So 225. So I'm just using the original value there. And this is going to give us so this chi-square value ends up being 364.09. So let me rewrite it here. Test statistic. It's going to be equal to a chi-square value of approximately 364.09. Now that, with respect to the position of the population, it's way out here. So automatically reject HO. And let me rewrite it as our main conclusion, reject HO. And you can just say because the test statistic of chi-square value, which is approximately 364.09, is greater than the critical value of the chi-square value of approximately 28.412 using C is equal to 0.90. So this will be our main conclusion. In this case, we're just basically looking at the critical region, and our critical value, it's a 28. The test statistic is way out here. It's on the shaded. It's on the reject HO. So that's actually it for this particular problem.